So suppose you have a function xy, function of xy. And let's say x is also a function of u and v. So I'll just put something like u, v. U for x, but then u plus 2v for y. And here's a question. Express partial derivative of f with respect to x, partial derivative of f with respect to y, and second partial of f with respect to x using second partial, or using variables u and v. Okay, so in other words, express it as partial derivatives of u and v. Okay. So the application of this, you'll see later, is to change a differential equation that's presented in one variable to be written again as a differential equation in a completely different variable. So you're going to see how it's applied in PD later. Okay? But I'm trying to do this separately as a review because it relies on multivariable chain rule, which you learned in multivariable calculus. And some of you may have taken that course like a year ago or more, so you might not remember it very well. So let's talk about that. To solve this question, first what you want to do is, since u is x and also 2v is y minus u, and because u is same as x, you have v equals to 1/2 y minus 1/2 x. And f is dependent on the variable x and y, but you can also say f depends on u and v as well, right? Okay. So if you view it this way, then it's like f depends on x and y depends on u and v. However, if you solve u and v in terms of x and y, now you have u and v as functions of x and y. Okay? And in such a case, we can write a dependence diagram. Here's the dependence diagram. F depends on u and v. Okay, now, f is a function of u and v. Of course, if you assign a value to u and v, then, I mean, if you have trouble imagining what a function of f could be, just let's say f is something like x squared plus 4xy plus y cubed, or something like that, some function of x and y, right? Then you can plug this u and u plus 2v into x and y, then it suddenly turns into a function of u and v, right? Okay. You can imagine that, right? Okay. And then u and v would be functions of x and y. As you can see, u is just a function of x, and v is a function of both x and y. So that's the dependence diagram. And from this dependence diagram, you can write down the multivariable chain rule as follows. So if you want to know how f changes when you change the value of x, and by the way, you have to know the meaning of this partial derivative. This partial derivative means you're fixing y, right? You're keeping y as a constant. You're only changing the values of x very slightly. So if you increase x ever so slightly, then it's going to change the value of u and v, which in turn will change the value of f, right? So it's a legitimate question to ask, how fast does f change when you change x ever so slightly? That's what partial derivative means, right? And the multivariable chain rule that you learned in Calculus 3 says that you just have to go through all the possible ways that x influences f. So there's one way that x influences f, which is change of x will bring change to the value of u, right? And then the change of value of u will bring change to value of f. That's one way that x influences f, going through this way, right? But then there's another way that the change of x influences f, which is change of x will bring change in y, in v, and then change in v will bring change in f. And that's called the multivariable chain rule. This actually happens a lot in economy. So if you take a course in macroeconomy, you do something like this. Like, let's say f is the price of food, some food, okay? And x is the price of oil. Now, if barrel of oil increases in price, then it's going to increase the production cost, because a lot of agricultural things rely on oil to run their machinery, right? Or even packaging their things uses oil, right? But not only that, it's also going to increase the transportation cost, right? Yeah. So this first one will measure how the food price will increase with respect to the increase in the production cost going through U, right? But then this one also says increasing the price of oil is going to influence the price of the transportation, and then you just measure how F is sensible with respect to the change in V. So you take this value, multiply them, and then the multivariable chain rule simply says you add them up, that gives you the total rate of change when you change the value of X. That's what this means, right? Is that good? Right. Now, on the other hand, because Y only influences V, Y doesn't influence U ever because U is just X. U doesn't depend on Y, right? So when you measure how F changes with respect to X, then this is just change of, with respect to Y, then this is change of Y will bring change to V only, and then change of V will bring change to F. And that's it in this case. Okay, and then we can compute further. What's round U round X? What's the rate of change of U with respect to X? 1, because U is just X. So if you differentiate U by X, it's just 1, right? So this will simply be change of F with respect to change of U. Okay. Times 1. Okay, and then change of F with respect to change of V. What is rate of change of V with respect to X? Well, V is this, right? If you differentiate by X, what do you get? Negative 1/2, right? So this will be negative 1/2. Okay. Now, we are going to frequently make use of an operator notation. So let me rewrite this first, because it's cumbersome to write round U. I'm going to use the simplified notation, which is just one single partial with U of F. And this one just, let's put minus 1/2 round of V F. Okay. And then we can further rewrite this in the operator notation, which is you kind of factor out the F outside. So you're thinking of this one as partial U minus 1/2 partial V applied to F. That's how you think about this. Okay. Okay, and for the same reason, what's round V round Y? What's the partial of V with respect to Y? 1/2, right? So it's 1/2 partial of v of f. Okay. And now the challenging part is, how do you represent the second derivative? See, already we finished the first two parts. So I've represented partial of f with respect to x in terms of u and v. So in terms of this new variable, it's round u minus 1/2 round v f. Again, why do we want that? Well, you'll see later when we apply it to PDEs, okay? And this is same as 1/2 round v f. So those are the things that we figured out. Now, how do we figure out second derivative of f with respect to x? Well, that's like taking this is taking two derivatives with respect to f. That's what it means. But I already know that one derivative is this thing, round u f. Well, I can write it like that, but let's just write it like that. Okay? So round u of f minus 1/2 round v of f. Okay. And then we can apply this rule again, except that instead of f, we have this complicated thing. Right? We can do that, right? So I'm applying this chain rule again because we're differentiating by x. It's exactly the same except that instead of f, we have this. Okay? So what that means is I have derivative with respect to u of f, but instead of f, we put this entire thing. Round u f minus 1/2 round v f times derivative of u with respect to x, plus the other one is derivative with respect to v of derivative u f minus 1/2 derivative v f times derivative of u with respect to y. No, not y, sorry. This should be derivative of v with respect to x. Right? I'm just writing this here. But then it's the same story, except, let me, right here. So if you have, derivatives are linear operators, right? So if you have derivative of two terms, you can differentiate one and then the other separately. Any constant multiple can be brought outside. So that one is going to be derivative of u squared, you differentiate twice with respect to u, minus 1/2 derivative of u, derivative of v, f. This is just 1, we already know that, right? And this is just equal to negative 1/2, that we already know, okay? So when you multiply these two, there is a minus 1/2 in front, so it would be negative 1/2 round v round u f, and then this times this with the negative 1/2 times negative 1/2 will be plus 1/4, so it will be 1/4 derivative of v squared of f. And then we can do one more simplification here. Did you know that second partials commute? Not always, there's some condition for it, but we're going to assume that f is differentiable many times, and in that case you can switch derivatives. Okay, so whether you differentiate by v first and then u, or differentiate by u first and then v, it's the same thing. Okay, so we switch one of them. I like uv better, so I'm going to just switch these two around. Then these are exactly the same. So this negative 1/2 and negative 1/2 will just add up, right? So the answer will be, I'll just write here. The answer will be second partial of f minus round u round v of f, and then plus 1/4 round v squared of f. You can also factor the f out and write in terms of an operator notation. but I guess I don't have to really write that. You should know. Okay, so that's how you do it.